Section 11.6 Absolute Convergence, Ratio, and Root Tests. A series is called absolutely convergent if a series of absolute values is convergent. So for example, let's say we have the series minus 1 to the n minus 1 over n squared. Well, then we look at the absolute values. So that's just the absolute value of minus 1 to the n minus 1 over n squared. And when we take the absolute value of the minus 1 to the n minus 1, well, it just becomes plus 1 for every term. All we're doing is taking each of these minuses that goes in between this alternating series and turning them into a plus, and all of the pluses in between are completely unaffected by the absolute value. So it doesn't matter that there's an exponent over here for the minus 1, it just removes that part of the series completely. So we just get the sum of 1 over n squared. It's just 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. All of the minuses become plus. So that's a p series. And p is equal to 2 because the exponent is 2, and 2 is bigger than 1, so this p series must converge. So that means that our series with the minus 1 to the n minus 1 in it is absolutely convergent. How about the series over n instead of n squared? Well, we do the same thing as before. We write it out with the absolute value. And that means that this minus 1 in the numerator is going to disappear and just become a 1. So we get the series 1 over n, which is 1 plus 1 half plus 1 third plus 1 fourth, and so on. And that's our old friend, the harmonic series, or a p series where p is equal to 1, which we know diverges. So that means that our series is not absolutely convergent. We don't have a definition for absolutely divergent, so we'll just say it's not absolutely convergent. A series is called conditionally convergent if it is convergent but not absolutely convergent. And then we have a theorem that if a series is absolutely convergent, then it is automatically convergent. So being absolutely convergent is even better than being convergent is a stronger condition. This should sort of make sense because remember when we looked at the alternating harmonic series and the alternating 1 over n squared series, we saw that both of those converged, even though for the regular harmonic series it does not converge. So having your absolute values converge is usually a little bit more tricky. Sometimes throwing in that minus 1 actually helps the series converge. So let's see if we can prove this real quick. We've got an, and we've got the absolute value of an. So that means that if an is negative, then this is 0, and if an is positive, then this is just 2 times it. So either way, it's going to be in between 0 and 2 times the absolute value of an. So if the sum is absolutely convergent, then the sum of the absolute values is convergent. So we can just throw it in 2, multiplied by constants, it'll still be convergent. And therefore, by the comparison test, the sum of an plus the absolute value must be convergent because it's smaller than this by this inequality. So being smaller than a convergent series means you converge. So we have the sum of an is equal to the sum of our convergent series minus the sum of the absolute values, which is also a convergent series because if you can think of these terms, then you can see they cancel out. Just leave you with sum of an. So our series is a difference of two convergent series. So the original series must be convergent. So whenever we have this guy being convergent, we automatically get this guy being convergent. So let's determine whether the series with a cosine of n over n squared is convergent or divergent. Well, notice over here for this series, it's not quite alternating, because even though the first term is positive and the second term is negative, the third term is also negative, and the fourth term is negative. But then the fifth term is positive, and the sixth term is positive, and the seventh term is positive. So our signs are changing somewhat irregularly. So this is like a pseudo-alternating series. It's just got a whole bunch of positive and negatives in there. It's not actually alternating though. So let's see whether this thing converges or diverges. Well, because we just did our new theorem, let's take a look at the absolute value of the series. If that converges, then we know that our series is absolutely convergent, and therefore it must converge, because absolutely convergent apparently implies a convergence. So we take a look at the absolute value of cosine of n over n squared, and cosine of n squared is already positive. N squared is already positive, so I just need to put the absolute value in the cosine, because that's the only thing that could possibly be negative. So we know that the absolute value of cosine has to be less than or equal to 1, because cosine, the most it could be is 1, and the least it could be is minus 1. And this is true for any possible n we plug in. So that means that the absolute value of cosine of n over n squared must be less than or equal to 1 over n squared. So that means that the sum of cosine of n over n squared must converge by the comparison test, because 1 over n squared converges. It's a convergence P series with P equals 2, which is bigger than 1, as we keep seeing. So that means that the sum of cosine of n over n squared without the absolute value is absolutely convergent, because if we were to take the absolute value, we see that it converges. And because the series is absolutely convergent, that implies that the series converges by the theorem that we just proved. So we get that the sum of cosine of n over n squared is convergent because it's absolutely convergent. So the definition of absolute convergence leads us into another test called the ratio test. If the limit of successive terms, when you divide them, is less than 1, then this implies that our series is absolutely convergent, and therefore, of course, convergent. So to see why this is true, consider that if this limit exists, that means that at some point along our sequence, for some value of n, we'll eventually have that the absolute value of an plus 1 over an is less than r, where r is just some number less than 1. Because if we go far enough, it has to be less than r if it's ever going to equal this limit, which is less than 1. So that means that if we go far enough, we'll have an plus 1 less than an times r. Just multiply both sides by the absolute value of an. So by the same logic, we could see that an plus 2 will be less than an plus 1 times r. However, we just said an plus 1 is less than an times r, so that means that this is less than an times r for this, but then times the r that's left. So that's an times r squared. So you could keep doing this and see that an plus 3 would be less than the absolute value of an times r cubed. So that means that if you go far enough along, the series starting at n plus 1 will be less than a geometric series. And notice that r is less than 1 because the limit is less than 1 by assumption. So the geometric series converges, and therefore our series an converges by the comparison test. Remember that it doesn't matter that we have a finite number of terms up until n that we haven't even looked at. It only matters that we go past an plus 1 and converge, because a finite number of terms at the beginning does not affect the convergence or divergence of our series. So if we take a look at the second part, if the absolute value of an plus 1 tends to a limit that is bigger than 1 or tends to infinity, then we can assume that at some point our terms will end up dividing and becoming greater than 1, because otherwise how could they ever approach a limit greater than 1? So at some point along our series this happens, which means that at some point along our series we end up with an plus 1 bigger than an, which means that our terms keep getting bigger, so the limit of these ans is not 0. So because the limit of ans is not 0, that means that our series diverges by the test for divergence. So we can see that if the limit is less than 1, it converges. If the limit is greater than 1, it diverges. But if the limit is exactly equal to 1, then you're not able to get convergence or divergence. And you can't see if anything happens to your series using the test. The test is actually completely worthless in that case, and you have to go and abandon it and use another test. You can't get any information at all. For example, if you were to look at the series 1 over n squared, you know that that series converges. If you look at the limit, you actually get that the limit of an plus 1 over an is equal to 1. So you could say, okay, well, that seems to imply that it works sometimes for convergent series. But no, that's not true, because if you look at the harmonic series 1 over n, you'll also get that the limit of an plus 1 over an is equal to 1. Those are two totally different series in terms of their convergence. So it doesn't tell you which one converges or which one diverges. It could be one either way. So be very careful if you hit that last case. Let's use the test right now to test the series n cubed over 3 to the n, where it alternates with minus 1 to the n. So we'll look at the absolute value of the next term over current term. So that's going to be minus 1 to the n plus 1 instead of n, because we're plugging in n plus 1 to get the next term. And instead of n cubed, it's n plus 1 cubed. And then instead of dividing by 3 to the n, we divide by 3 to the n plus 1. And we'll divide that by the term without plugging in n plus 1, so that's just plugging in n. So we take the absolute value of this, and dividing by a fraction is the same as multiplying by the reciprocal. I also notice that taking the absolute value only gets rid of this minus, because everything else there is positive, because n starts at 1. So we have n plus 1 cubed over 3 to the n plus 1 times the reciprocal 3 to the n over n cubed, because we divided by this, so we just flipped it. So this is equal to 1/3 times n plus 1 over n cubed, because we just have 3 to the n cancel with 3 to the n, we just have a 3 left. And then we can take out the cube because we have n plus 1 over n cubed. So this equals 1/3 times 1 plus 1 over n to the third, because we can just separate the fraction. N over n is 1, 1 over n. And it looks like as n goes to infinity, this stays at 1, this goes to 0, 1 cubed is 1, so this entire thing goes to 1/3, which is less than 1. So that means that our sum is absolutely convergent by the ratio test. So the ratio test is kind of cool because none of the other tests we've done so far have given us absolute convergence, which we get for free with the ratio test, which remember is even stronger than convergence, because it tells us that our series is not only convergent, but even the absolute values of our series converge. Okay, how about n to the n over n factorial? So notice we don't need the absolute values in this case because the numerator and denominator are both positive, because we started at n equals 1. So this is just n plus 1 to the n plus 1 all over n plus 1 factorial, because we plug in n plus 1 instead of n, and then we divide by n factorial, n to the n over n factorial, but dividing by that is the same as multiplying by the reciprocal, so we multiply by n factorial over n to the n. So then this is the same thing as saying it's n plus 1 times n plus 1 to the n. Just pull out one of these n plus 1s. You could think of that maybe in terms of the laws of exponents. This is just n plus 1 to the n times n plus 1 to the 1. So then in my denominator, I have n plus 1 times n factorial. Remember, I can always pull out the last term in a factorial to get the preceding factorial. So then we keep our n factorial over n to the n that we were multiplying by before. And it looks like we have a lot of cancellations. N factorial cancels n factorial, and our n plus 1 cancels with n plus 1. So we just have n plus 1 over n, and we can take out the n. So we have n plus 1 over n to the n. Well, that's the same as 1 plus 1 over n to the n. So I just pull out the fraction to separate it. So 1 plus 1 over n, that should look very familiar. If we take the limit as n goes to infinity, this is exactly how we define the number e. And e is bigger than 1. So it looks like our series definitely diverges, because our ratio test said that if we went to a limit and the limit was bigger than 1, not equal to 1, then our series diverged. Next up, we have the root test. The root test is so similar to the ratio test. The proof is very similar also. If the limit of the nth root of the nth term is less than 1, then our series is absolutely convergent. You can see this by taking the nth root of some term an, because at some point along the sequence, if the limit is less than 1, then this will have to be less than r, or r is some value less than 1. By the same logic as before, you do this successfully for your next bunch of terms, and you get that your series is less than a convergent geometric series, and therefore converges. Similarly, for the divergent case, you look at terms far enough along such that you get that the nth root is bigger than 1, which means that your limit of your ans does not tend to 0, so your series diverges by the test for divergence. And then by the same reasoning as the ratio test, the limit of the nth root equaling 1 gives you no information whatsoever. So if you end up taking the nth root and the limit equals 1, then you should stop and find another test. And by finding another test, I mean find a completely different test. Don't just try using the ratio test, because the ratio test is also going to give you a limit of 1 and be inconclusive. They're both tied together like that. Similarly, if you were trying a ratio test and you got that the limit of the ratios is 1, so your ratio test is inconclusive, then don't try the root test, because if you take the nth root, that'll also end up being 1. So let's use the root test really quick. Notice that candidates for the root test, or good candidates for the root test, are ones that have some sort of exponent of n in there, because then when you take the nth root, it'll disappear to make your series a lot easier to deal with. So we have an equal to 2n plus 3 over 3n plus 2 to the n. So the nth root is super nice. It's just going to be 2n plus 3 over 3n plus 2 without our exponent. So we can divide the numerator and denominator by n. We get 2 plus 3 over n over 3 plus 2 over n. And it looks like as we go to infinity, these guys go to 0. So our limit is going to be 2/3, which is smaller than 1. So that means that our series is absolutely convergent by the ratio test. I said ratio test, I meant root test. They're both so similar. Lastly, by a rearrangement of an infinite series, we mean a series obtained by simply changing the order of the terms. So we just take a series, we write it out, we move the order somewhere else, but we keep all the terms the same. Turns out, if our series is an absolutely convergent series with some sum s, then rearranging it has no effect on the sum whatsoever, which is kind of what you would expect. What's more interesting is that if you have a conditionally convergent series and r is any real number whatsoever, there happens to be rearrangement of that series that has a sum equal to r. So if you don't have absolute convergence, but you do have conditional convergence, then you can end up manipulating your series to equal anything you could possibly want. So that's kind of ridiculous, but it turns out if we multiply the alternating harmonic series, which we know converges, but we also know that it's not absolutely convergent because the absolute value is the harmonic series, which diverges. So if we take that alternating harmonic series and we multiply by a half, then notice the 1 becomes a half, and the minus 1/2 becomes minus 1/4, 1/3 becomes 1/6, and so on. So instead of equaling ln2, this series will equal half ln2. We insert a whole bunch of zeros in between the terms of the series. So we put a 0 over here, 0 over here, 0 over here, all between them. And then we add it back to our alternating harmonic series. So we get 1 plus 0 gives you 1. We get minus 1/2 plus 1/2 gives you 0. And then 1/3 plus 0 gives you 1/3, and so on. You keep doing this and you get the series 1 plus 1/3 minus 1/2 plus 1/5 plus 1/7 minus 1/4. Eventually this minus 1/6 will show up again. You'll get all of the exact terms that you had with your original alternating harmonic series. But now it equals ln2 plus half ln2, which is 3 over 2 ln2. So we got the exact same terms in the alternating harmonic series as we had before, but we now have a rearrangement of those terms with a completely different sum.